What up? I've woken up from my slumber and I've emerged anew on the other side of my first quarter UCSB. On today's menu, I've cooked up something that will grant y'all the base necessary to tangibly understand relatedness tests. Like really feel them up in your noggin. Settle in and make a nice little home in there. Are you ready for that? Well, I hope so, because we're gonna get started very... Okay, so let's start with the assumption that in America, 4% of the population plays outdoor soccer at least once a month. I'm representing the population that plays soccer with a variable p for play. In statistics language, the probability of p, or p of p, is 4%. Knowing the percentage that do play outdoor soccer at least once a month, we also know the percentage that do not play. This other group completes the first group and is considered the complement to p. In this case, p of p complement is 96%. I like visually representing this kind of information because, like in many fields, statistics uses a lot of numbers and terms that aren't part of the typical everyday vernacular. This rectangle over here uses area to represent probability. The leftmost portion represents the 4% of the population that are consistent soccer players, and the empty portion are those that aren't. Hold up. I'm getting news from independent sources telling me that 30% of Americans rate blue as being the most appealing color. I'm going to assign the variable b to represent the group of people who prefer blue. This means that p of b is 30%, and because we know p of b, we also know that p of b complement is 70%. Wouldn't it be nice if I can represent both of these statistics at the same time? Great question, hypothetical viewer, and boy, do I have the technology for you. On the right over here is a two-way table that correctly shows probability using a representative amount of area. And because somebody can play soccer regularly and find blue to be the most appealing color at the same time, there's a region of overlap in the bottom left portion of the square outline for you. This region is important for other reasons, but I'll get into that later. One thing to take into account is the assumption that these events are independent relative to each other. This means that the probability of finding blue the most appealing color is 30% regardless if you play soccer or not. The reason I like to use this table over something like a Venn diagram is its relationship with a multiplication rule of probability. Say, for some reason I wanted to roll 2 3s in a row on a die. The probability of doing that is 1 of 36 because you only have a 1 in 6 chance to roll a 3, but you have to take 1/6 of that probability because you're rolling the die a second time. This rule maps well into the table because area is found by multiplying side lengths. If side lengths correspond to single event probability, that makes area a great visual aid for representing 2 event probability. By multiplying the values of p of p and p of b together, I found that the probability of playing soccer and liking blue to be 1.2%. This same method can be used to find the probabilities for each other quadrant. Everybody should fall under at least one of these categories, so the sum of the probabilities should add to 100%, and after checking, they do. Okay, here's a similar but not quite the same problem. Let's imagine a population of 10,000 people and say that 8% of them have a soccer ball in their home. That's all right and good so far? Just make a table with a single cut separating the 800 that have a soccer ball and the 9,200 that do not. Represent the group with the ball with a variable b, but this time it's a lowercase b because uppercase b has already been taken. Okay, let's try making a two-way table with this new information combined with the previous stats on regular soccer players. Okay, here's the table with the given probabilities. Let's use the multiplication rule to find the probabilities of each given region and wham! Bet you weren't expecting that. Well, the probability of each region, smallest to largest, is 0.32% for the group that plays soccer and owns a soccer ball, 3.68% for those that play soccer but don't own a soccer ball. Blammo! Whoa, got you again there. Nah, just kidding. Just making sure you're prepared. I hear there's a crazy guy out there trying to scare people with sled and slide transitions. Better now? Great. To find the number of people that each region represents, just multiply that region's probability by the total number of people. Just like that, we can categorize every last person in our population. Just like last time, the checksum is 100%, but the total number of people should add to 10,000 as well. But there's an issue. Take a closer look. The problem here is relatedness. Without using any math at all yet, I can tell you that the people who play soccer regularly are more likely to own a soccer ball than those that don't. So what are the different ways to represent the relatedness of these two events? One way to categorize this relationship is by using one group as a test for the other group, but not like a test you get a score on at school. A predictive test, something like a cancer screening test. There should be an explanatory group that is independent, and there should also be a response or test group that is dependent on the explanatory group. Well, in this case, it's clear that being a soccer player makes you more likely to own a soccer ball and not the other way around, but that won't always be the case. If you ask the question, knowing that one is a soccer player, how often will they own a soccer ball, the number you get is called sensitivity, and is one of the most direct ways of measuring correlation. So, what is the sensitivity of our soccer ball test? For this problem, the test has a sensitivity of 0.8, or 80%. That means if we narrow our view to only look at the 4% of soccer players in our population, 80% of them will also own a soccer ball. In more formal terms, this is known as the conditional probability, and it's almost always used with the word given. You can say the same information more succinctly with the phrase, the probability of B given P is 80%. The only thing that changed between last example and this new one is that we now know the conditional probability for soccer ball ownership. Using only the information we have right now, we have what we need to fill out the rest of the table. We just need to use the intersection formula for dependent events. Because probability and area are related when using this table, you can also think of it as an area finding formula. First, limit our view to only look at the 4% of soccer players. Then take an 80% of the cut of the already reduced region to find where the two events overlap. 4% times 80% is 3.2%. If we multiply that value by 10,000, we know that there are 320 people that play soccer and own a soccer ball. This is 10 times more people than before when we assumed that these two events were unrelated. Now on to finding the area of the other regions. Remember how I mentioned that finding the area of the overlapping region would be important at 1 minute 50 seconds? This is where knowing that information comes in handy. We know that 400 people play soccer regularly, and splitting that group into people that do own a soccer ball and those that don't does not change that fact. All subsets should still add to 400 people. Because we know that 300 people play soccer and own a soccer ball, that means that 80 people play soccer and do not own a soccer ball. We can do the same thing for the group of people that have a soccer ball to find that 480 people have a soccer ball but do not play regularly. Finally, we know that all 9,120 people not accounted for yet do not play soccer or own a soccer ball. Using only the percentage of people that fall under each group and the sensitivity of our test, we are able to fill out the entire table. Here's something interesting that I came across. Is it always better to have a more sensitive test? You would think so, right? I want my test to detect every instance of the thing it's testing for. Well, Sharpie is a perfectly sensitive heart disease screening test because it will leave a mark on every affected person. It will also leave a mark on all the people without the disease too, so it isn't really that good of a test. Because of this, there are 3 other terms commonly used to describe how effective a test is. Is that too many terms? Well, it's good to be specific because these kind of tests are used a lot in medicine and disease screening. We already learned about sensitivity, but there's also its counterpart, specificity. It asks, knowing that one does not have a disease, how often will the test show negative? Having a test be both sensitive and specific would be the best, but these two terms are counterparts of sorts, and making a test more sensitive will often make it less specific. This is why designing a test to fit its purpose is so important. You really don't want to miss a case of cancer, so it might be better for cancer screening tests to be more sensitive. On the other hand, it would be bad to incorrectly mark somebody as positive in the drug test, so it might be better for a drug test to be more specific. The thing about sensitivity and specificity is that they tell you how often a test will be accurate. Which is nice, but we have to know whether or not somebody has a disease for them to be useful. Most of the time, we want the opposite. We want to know our likelihood of having the disease when we get a positive test. This is where our next term comes in, positive predictive value. It's actually super easy to understand too. When given a positive test, PPV tells us how often the test is correct. Because we know that the test showed a positive result, we can limit our view to only show the top 2 boxes, true positives and false positives. Then, we know that our probability of actually having the disease is the number of true positives over the sum of both boxes. Negative predictive value does the same thing but for negative tests. Given a negative test, NPV tells us how often the test is correct. A perfect test will score high in all 4 terms: sensitivity, specificity, positive predictive value, and negative predictive value. But since that isn't always possible, a good test will strike a balance of these terms fitting for its purpose. So we know how to interpret tests now, right? If I take a test and it turns out positive, look at positive predictive value for answers. Well, yeah, but how does one find positive predictive value? PPV can be expressed in at least 3 different ways. It can be conditional probability, using the phrase probability of disease given positive test. If you know the number of people in every region, it can be a ratio involving true positives and false positives. But if you don't have the group size, but you are given basic probabilities, use Bayes' theorem. They're actually the same formula, but use different starting information to get your answer. Let's try it out. Let's quantify how good our soccer ball test is using the same numbers from earlier. I left out the number of people in each region because we don't need that right now. We do need the probability that one is a regular soccer player, the probability that one owns a soccer ball, and the test sensitivity. I think that's kind of neat. Along with the basic probabilities, you only need the test sensitivity to find PPV. By putting these probabilities in their corresponding places, we know that the chances of playing soccer, given that one passes the soccer ball test, is 40%. That must mean it's not actually that good of a test. Or is it? What does it mean to have a good test? Because knowing that they passed the soccer ball ownership test actually tells you that their odds of playing soccer regularly went up by a factor of 16. To understand where these values are coming from, we're going to have to take a step back and understand what a test really does. If you go to the doctor and they ask, does your family have a history of heart disease? They ask these kind of questions not to tell you that you'll for sure have a heart attack. They don't even ask these kind of questions to discover your chances of having a heart attack. These screening tests should be thought of as tools to update the odds of the thing that they are testing for. People in the United States have one likelihood of having a heart attack, but a good test question will separate the whole population into groups, one with somewhat higher odds and the other with somewhat lower odds than before. The factor by which these groups are updated up and down tells you how strong these test is. The trick is finding that number. This method of thinking about tests as a tool to update prior odds is known as Bayesian statistics. Where Bayes' theorem finds PPV directly, another formula attributed to Thomas Bayes finds both positive predictive value and the updating factor that tells you the strength of the test, the Bayes factor. This updating factor is also known by another name, the positive likelihood ratio. There's one problem though. This method was a little odd. No, really, if you want to update your prior more than once, the formula using probability is much more complicated, which is why we convert to odds. So what's the difference between probability and odds? Well, both terms represent the exact same information: number of successes, number of failures, and combined total. The thing is, you only need two numbers to find the third, so which two do you choose? Probability chooses number of successes and the total, but odds chooses the number of successes and the number of failures. Really, is that simple. Probability is used more commonly in everyday life because it runs on a 0 to 1 scale that can easily be converted into a percent. Again, the formula finds positive predictive value in terms of odds by multiplying the prior by the Bayes factor. On the left side of the formula, positive predictive value in terms of odds shows the ratio of true positives to false negatives. And by using clever algebra, you can find this ratio by knowing the sensitivity and specificity in terms of probability and the prior in terms of odds. Got it? Great. Let's put it into practice. I've made an experiment involving cheap and expensive Pinot Noir and sommelier's ability to distinguish them. The experts are asked to tell the cheaper wines from the expensive version, but only the experimenters know that there is one bottle of expensive wine and 4 of the cheaper ones. Before the sommeliers test the wine, we know that the odds of picking the expensive version is 1 to 4. This is the same thing as saying that the prior odds are 1 to 4. To find the Bayes factor, we're going to need more data. Okay, when given an expensive wine, a sommelier will correctly identify it 90% of the time. This is known as the test sensitivity. When given a cheaper wine, the sommelier will correctly label it 88% of the time. This is known as the test specificity. When putting everything into our formula, we can find the test Bayes factor. And kablamo! The Bayes factor for this test is 7.5. That means if an expert thought that a wine was expensive, their intuition odds is 7.5 times better than random chance would suggest. This turns our 1 to 4 odds into 7.5 to 4 odds. In percentage, this correlates to an upgrade from 20% to about 65% likelihood that a wine is expensive. The great thing about Bayes factors is repeatability. You can ask 2 experts, and if they both agree that a wine is expensive, you now have a 56.25 to 4 odds. This equates to about 93% certainty. The last thing I want you to know about is the opposite of Bayes factor. If Bayes factor is also known as a positive likelihood ratio, this is the negative likelihood ratio. It uses a very similar formula, but instead of finding the odd equivalent of positive predictive value, it finds the odd equivalent of negative predictive value. This time, the lower the negative likelihood ratio is, the better. Putting the values in the correct places, we can find the negative likelihood ratio is about 0.114. Just like the Bayes factor, it is used to update the prior. So if a wine expert says that a tested wine is not expensive, the odds of it being expensive go down to 0.114 to 4, which is about the same as saying that the chances went from a 20% to 2.8%. Again, it's the magnitude of change that tells you the strength of the test. Woo! Finally, what you've all been waiting for. Review questions. You've got a lot to go over, so make sure to pause if you want to find the answers on your own. Calculators are allowed, so don't feel bad if you need to use one. First question. If I've rolled 2 dice, how often are they expected to sum to 3? Answer? Answer is B. 2 dice rolled out of 36 outcomes, but there are only 2 paths to get them to sum to 3. Rolling a 1 then a 2, or rolling a 2 then a 1. Next question. If 72 people roll 2 dice, how many people are expected to have their dice sum to 3? The answer is C. Each individual has a 2 in 36 chance of getting 3, but there are 72 people. All the individual probabilities summed together show that 4 people are expected to have their dice sum to 3. These next questions are based on the dependent events lines. Okay, if greater than 10 hours of studying is correlated with the test score above 80%, what should be the response test group? This is opposed to the explanatory group, which should be the independent variable and explain the response test group. The answer to this question is B. Both groups are correlated with each other, but greater studying explains test scores, not the other way around, making test scores a response test group. Next question. An accurate test should have many true positives and true negatives, or many false positives and false negatives. The answer is A. Hopefully this one wasn't too bad. An accurate test should result in many true results and fewer false ones. These next two questions involve conditional probability. The first one asks, what does P of A given B equals 70% indicate? I'm going to spoil the answer in a couple seconds, and the answer is D. This one's going to be a little tricky, because C also looks like it can be true. Though there's actually one case where C isn't true. If the probability for A is 70%, that would make A independent of B, because its probability is the same regardless of if B is true or not. The next question asks, if P of A given B equals 70%, and there are 14 people within the overlap of A and B, how many people fall under B but not A? Yep, this one might need a pencil and paper to work out, but I'm sure you got it. Got it? The answer for this one is A. Imagine that the 14 people overlapping in both A and B represent 70% of B's total area. To find the total area of B, multiply by the inverse of 70% to get 20. Then take 30% of the total to find the non-overlapping region of B, getting an answer of 6. These next questions are related to defining positive predictive values lines. The first question asks, what does a positive predictive value of 80% indicate? The answer for this one is C. This question just asks for the definition of positive predictive value. Another question asks, using Bayes' theorem, if P of B given A equals 70%, P of A equals 50%, and P of B equals 40%, what is P of A given B? Then, towards the bottom, I provide Bayes' theorem for you. The answer for this one is C. Putting the values in the right places should be enough to get this question right. These next questions are related to the Bayes factors lines. The first question asks, what probability is equivalent to 3 to 4 odds? The answer to this question is A. Odds show successes and failures, but probability shows successes in the combined total. To convert, just add the two terms from odds and replace the second number with the new one. The next question asks, what does a Bayes factor of 1 indicate? Well, what does it mean? The answer is B. In context, if the prior gets updated by a factor of 1, that means it doesn't change at all, and the test tells you nothing. This last question is basically the entire reason I made this video. I wanted to know how many positive tests you would need to disregard a single negative test. Turns out the answer was a lot more complicated than I initially anticipated, but oh well, here it goes. The question asks, what is the minimum number of small yays in agreement that a wine is expensive to say with above a 95% confidence that the wine is in fact expensive if one expert already believes it to be cheap? The prior odds are 1 to 4, the test has a Bayes factor of 7.5 and a negative likelihood ratio of 0.114. These numbers look familiar because of the same values from the test from earlier. The answer to this question is D. To find the answer, I first converted 95% probability into odds with 4 as the number of failures. This turns out to be 76 to 4 odds. This means that I need my posterior odds to be at least that amount. I found the threshold number of experts in agreement to be about 3.23 using logarithms, but honestly you can just guess and check. Round this value up because you can't have a partial expert and you get an answer of 4. Thank you all for listening, and remember, the mitochondria is the powerhouse of the cell.